Do you know what stars are made of? Nowadays, it's pretty common knowledge that stars are mostly made up of hydrogen and helium, but this wasn't always known. In fact, for a while, astronomers and astrophysicists believed they were made of completely different elements. This is where the story of Cecilia Payne-Gaposchkin comes into play. In her 1925 thesis, which was once referred to by astronomer Otto Struve as the most brilliant PhD thesis ever written in astronomy, she demonstrated that hydrogen and helium compose the majority of a star's mass. Payne's career in astronomy faced many barriers and hurdles, just as a lot of women have experienced in scientific fields. Today, we'll take a look at how she unveiled what the universe is made of. Cecilia Payne was born in Wendover, England on May 10, 1900. Her father died when she was 4, and her mother, seeing that her daughter had an interest in science, enrolled her in a private school that was well equipped to teach the subject. In 1919, Payne entered the Newnham College at the University of Cambridge on a scholarship. There, she studied botany, physics, and chemistry, despite the fact that the university didn't offer degrees to women at this time. As the only woman in her class, Payne often felt mocked and humiliated by her professor and male students. This was only the beginning of the struggles she would face due to being a woman. For a time, Payne was uncertain which field of science she wanted to commit to. Then, by chance, she heard Arthur Eddington give a public lecture about his trip to view the 1919 solar eclipse. This observation helped prove Albert Einstein's theory of general relativity. After hearing Eddington's lecture, Payne was utterly fascinated by it, and this helped her realize that physics was for her. Later, the Cambridge Observatory held an open night for the public. Payne attended it and asked so many questions that the staff fetched Eddington himself. He recommended some books she could read, but she had already read all of them. So he instead invited her to use the observatory's library, which gave her access to all of the latest astronomical journals. However, Payne realized early into her time at Cambridge that women had little to no hope of advancing past a teaching role, and no chance at all of earning an advanced degree. Luck came her way when she met Harlow Shapley, the director of the Harvard College Observatory, during his trip to the UK. Because of Eddington's glowing recommendation, Shapley offered Payne a graduate fellowship. She accepted, and in 1923, she sailed to the United States to continue her education. By the time Payne arrived at Harvard, women had already long since contributed to research at the Harvard College Observatory. In the 1870s, the director began hiring women that became known as the Harvard computers. Computer in the sense of someone who does math and calculations, not in the sense of the machines that we think of today. The job of the Harvard computers was to sort through and process data. Women were preferred for this job because they were assumed to be more patient for it than men, but they could also be paid lower wages than men. Payne herself was never a Harvard computer, but her eventual work did relate closely to the work of one of them, that being Annie Jump Cannon. Cannon had made a classification system for stars that sorted them into 7 categories based on their spectral type. These were also thought to correlate to the star's surface temperatures, but no one could prove this quantitatively. At least, not yet. It had been known since the mid-19th century that each element produced a unique pattern of spectral lines, a sort of fingerprint that you could use to identify them. This was true of stars. Different stars displayed different spectral lines. Harvard had the world's largest archive of stellar spectra on photographic plates. These were obtained by attaching a spectroscope to a telescope. This tool would spread the light of a star into a complete rainbow of colors spanning all wavelengths of light. A typical stellar spectrum has many narrow, dark gaps where light at a particular wavelength is missing. These are absorption lines, and they result from elements in a star's atmosphere absorbing the light coming from hotter regions below. In theory, the compositions of stars could be obtained by simply comparing their spectral lines to those of known elements observed in laboratory spectra. By doing this, astronomers identified elements like calcium and iron as responsible for some of the most prominent lines. So naturally, they concluded that these heavy elements must make up the majority of stars. This also meant they concluded the visibility visible universe was made of many of the same elements as Earth. By the time Payne arrived at Harvard, a comprehensive study of stellar spectra was already underway. Canon had sorted stars into 7 categories, and many astronomers had just accepted that stars were made of the same things as Earth. But Payne had studied quantum physics, and she knew about the work of Indian physicist Meghnad Saha. Saha had researched the relationship between temperatures, the quantum states of hot atoms, and spectral lines. This meant Payne knew the spectral lines of ionized atoms, such as those that would exist in the extremely hot atmosphere of a star, differed from the spectral lines of neutral atoms of the same type. In her PhD work, Payne combined data on quantum energy levels for elements with Saha's theory, and this allowed her to fully interpret Canon's classification scheme. A significant outcome of her research was the correlation between a star's category and its surface temperature. This part of Payne's thesis was well received. It sort of confirmed what a lot of people already suspected. But another part of it, not so much. Payne's work showed that the wide variation in stellar spectra was due mainly to the different ionization states of atoms, and therefore to the different surface temperatures of stars, and not to different amounts of elements. In fact, she went and calculated the relative amounts of 18 different elements. It was these calculations that discovered the sun and other stars are made almost entirely of hydrogen and helium. Hydrogen was 1,000,000 times more abundant, and hydrogen 1,000 times more than any other element. All the heavier elements that people previously assumed stars were made of, well, those made up less than 2% of the mass of stars. Payne's discovery was revolutionary. Shapley sent her thesis, which she completed in 1925, to Henry Norris Russell, the director of the Princeton Observatory. However, Russell wasn't on board with what Payne found. He informed her that her result is clearly impossible. Because her thesis just wouldn't be accepted without Russell's approval, Payne inserted a statement into the final version of the thesis saying that the calculated abundances for hydrogen and helium were almost certainly not real. This was a decision she would come to regret. Later in her life, Payne would admit that she wished she had stood behind her conclusions more firmly. And then, in 1929, Russell published his own derivation of the abundance of different elements in stars using a different method. This only confirmed Payne's discovery. Stars were made mostly of hydrogen and helium. He cited her work, which sort of indirectly confirmed she was the first person to make this discovery, but he never mentioned that he originally rejected her idea. Though he wasn't the first to make the discovery, Russell's work paved the way for astronomers to accept this new model of the universe, so he became more credited with it. Payne, for her part, actually praised Russell's work. Her only frustration was with herself for not standing up for her thesis. Luckily, time was kind to her, and she is now more remembered as the one who discovered what stars are made of. Payne remained at the Harvard Observatory under Shapley after completing her thesis. She advised students, conducted research, and gave lectures, all of which were the usual duties of a professor. However, because she was a woman, her only title was that of a technical assistant. Shapley tried to get this changed, but the guy making the decisions was extremely sexist and refused to give Payne the title and responsibilities she deserved. Payne continued her stellar spectral work with a book titled Stars of High Luminosity, which focused on Cepheid variables. This marked the beginning of her interest in variable stars and novae. She contributed a lot to the physical understanding of variable stars. A lot of this work was done alongside Russian astronomer Sergei Gaposchkin, whom she married in 1934. In 1956, Payne finally became the first woman to become a professor at Harvard. Just a few months later, she became the chair of the astronomy department, which also made her the first woman to head a department at Harvard. Payne retired from teaching in 1966, but continued her research work for another decade or so. On December 7th, 1979, she passed away at 79 years old. Cecilia Payne wasn't well recognized during a majority of her professional career. Her groundbreaking thesis went against what was commonly believed at the time, and even though it later turned out she was right, for a long time after, she wasn't given the proper credit for her discovery. Payne might be one of the most important figures in astronomy, and certainly in specifically the study of stars. She didn't just discover what stars are made of, she effectively found out what most of the visible universe is made of. Hydrogen and helium are the most abundant elements in the universe, and this helps us better understand the world that we live in. I hope you enjoyed this little exploration of Cecilia Payne's work. If you did, I'd appreciate it if you could leave a like or even subscribe if you want to see more. This was my second video for Women's History Month, and the first one was about Carolyn Shoemaker, so you should go check that one out too. And there will be a third before the month is over, mark my words. Thank you very much for watching, and I'll see you next time.